I suggest we settle down and we start. Hi, good morning. Yes.
Last session you said that the diagonal elements of the matrix are related to self-regulation of the species and are taken to be -1. I want you to a little bit more explain about that.
Okay.
What is self-regulation and why -1?
Okay, very good. I'll answer it as soon as people. Okay, let's settle down and start. Okay, so I would like to begin by addressing a question from one of the students. And what she asked was, we talked yesterday about the diagonal elements of this community matrix. And we said they're -1. So the question was, what is this self-regulation and why -1, right? Okay, so first of all, why -1? Well, this is an arbitrary choice. We could put -2 or -10. It just sets a scale. Okay, and in fact, the numbers don't have to be identical. You can draw from, for example, a Gaussian distribution that is centered at -1, and that would also give you the same behavior, right? So it's an asymptotic thing that on average it's -1. Okay, so the 1, there's nothing special about the 1. It just, if we put anything else but 1, we would have to scale things, right? So it's just a way for us to remove one parameter. But then why minus, and what is the self-regulation? Okay, so we were talking about the change from the steady state value. Okay, and the diagonal elements, what they mean is that left to their own devices without the interaction with the other species, so if each species just follows its own growth, then it will tend to a steady state value, to that same steady state value, right? This is the negative part in the diagonal. Now, why is this reasonable? Well, if we think about, for example, the chemostat, right, then we reach a situation of nutrient limitation, and then the species reach a steady state between their consumption and the supply, right? More generally, one can think about this as the carrying capacity of the ecosystem, which is something that we'll discuss today in the context of the generalized Lotko-Volterra models, right? So this could be competition not just for nutrient, it could be competition for space, for example, or, the trees in the rainforest compete for sunlight, okay, which is also, I guess, a form of nutrient, right, in this context. So I would say that the self-regulation is just the manifestation of the reality that living things live under constraints. Not everything is infinitely abundant. And therefore, these constraints mean that they cannot grow beyond a certain point, okay? But it means they can grow usually to this carrying capacity, right, left to their own devices, right? So having the negative in the diagonal means that they will tend towards this steady state value if undisturbed by the off-diagonal elements. Okay, so I hope I answered your question. Good, so we still need to finish up this Robert May chapter before we move on to the generalized logical Volterra. So I've updated the notes. This time, actually, chapters 1 and 2 have been left untouched, but chapter 3 has appeared in the new PDF. Right? So today we'll talk mostly about chapter 3, but let's finish chapter 2. Right, so we finished yesterday with this magical formula, right, May's stability criterion. And we said how much of a paradigm shift this was in terms of how people understood the stability of systems in general and ecosystems in particular, right? That as things become more connected, or as the connection strength increases, or even just as the number of species increases, right, then you tend towards a situation where you would have one positive eigenvalue of the system, which would take it away from this specific steady state. And I'll come back to this emphasis about this specific steady state in a few minutes, but before that, I would like to generalize, or rather to connect two extremes that we discussed with regards to the random matrix, right? So we started off with Wigner's result for the symmetric Hamiltonian, okay? And according to Wigner, right, which included a symmetric, it doesn't have an E, yeah, which was a symmetric matrix, then the support was from -2 sigma to +2 sigma. Okay, but then when we talked about the Ginebra-Gierko disk, and there's a bunch of other people involved in this. Like I said, this is a work in progress. Terence Tao made important contributions about this rather recently, I think, in the last decade or so, for example. So I apologize for all the people that I'm not crediting when I call it the Ginebra-Gierko, right? But here the support was essentially minus sigma to plus sigma, right, on the real axis. Okay, and here this was completely random. Right, so we went from a fully symmetric to a completely random, and actually the support shrank, right? And in fact, Robert May's result lies on this side of the completely random. But what if there are some correlations, right? What if the correlation coefficient between matrix elements is not 0 and is not 1? So there is a general formula called the elliptic law, because it describes an ellipse rather than a circle. And what it says is that the real component of the eigenvalues divided by sigma squared 1 plus rho squared plus the imaginary component of the eigenvalues divided by sigma squared 1 minus rho squared is less than or equal to 1. And here I'm neglecting C, right? So we're taking C to be 1, and the matrix has already been normalized by 1 over root n, so that n has disappeared as well, right? We don't want to carry all these constants for this discussion. Okay, where, to be very specific, this rho, this correlation coefficient, right, is when I look at an element aij and an element aji in the matrix, on average, right, so the expectation value of this pair, and this would be rho sigma squared over n. Here we see the 1 over root n that manifests as the 1 over n. Okay, so what we're seeing here is a situation where we could have any correlation coefficient that we want, going from -1, which is a fully antisymmetric matrix, to 0, which is a completely random, uncorrelated matrix, to +1, which is a fully symmetric matrix. Okay, so how does this make sense? Well, a fully symmetric matrix, we might worry about this part, right? Because 1 minus rho squared would be 0, except that a fully symmetric matrix has only real eigenvalues, so we don't have to worry about this at all. Okay, and what we have lambda squared divided by sigma squared times 2. Sorry. Yes, that's a big mistake, but it's been fixed. Good. Sigma squared 2 squared, right? This gives us the support of -2 sigma to +2 sigma, right? Lambda squared, sigma squared, 2 squared, right? Or lambda is between 2 sigma, -2 sigma and +2 sigma, right? So if we have a full symmetry, rho equals 1, then we get Wigner's law, right? By plugging in rho equals 0, what we have is exactly the circle. The real part squared plus the imaginary part squared is less than or equal to sigma squared, right? So we're back to the Ginebra disk. If we have actually a fully antisymmetric case, right, so rho is -1, then we might worry about this going to 0, except an antisymmetric matrix has only imaginary eigenvalues, and therefore this doesn't exist, and we basically retrieve the same kind of answer, but in the imaginary space and not in the real space, right? And of course, one can put any arbitrary correlation coefficient here and get the required relation, which in general is an ellipse. So hopefully this now extends between these two situations where it's completely unreasonable for ecosystems to be fully symmetric, because, you know, to say it a little bit bluntly, this would mean that the lion eats the zebra at the same rate that the zebra eats the lion. Okay, not very likely, yeah? But on the other hand, also it's not very likely for a system to be completely random. And we'll discuss that basically in the generalized Lotka-Volterra part just a little bit later today. Yes?
It might not be very related, but I wanted to ask, like, the example you said, the lion eats the zebra. If the lion eats too many zebras, there are not enough zebras, and the lion will die out as well.
So this is when what will bring us to the generalized Lotka-Volterra, right, or predator-prey relations, yeah? But I remind you that so far, and this actually leads to a very important point, right? So far, the May description is only a linearized description about the fixed point. This is not a full description of the dynamics, okay? This is looking at first-order Taylor expansion of the dynamical system about its fixed point, right? And this is actually why one must be careful applying May's principle sort of blindly. So just one more thing I'd like to mention before we philosophize a little bit about this. We can decompose the matrix into blocks. Right? So we can think about a system which is composed of species who live in subspaces and only interact within that subspace with each other, right? So we have, you know, one subspace here, another subspace here. These are zeros, Okay, maybe I shouldn't have put 0 here. One subspace, second subspace. Okay, so we can decompose the matrix into blocks, and this is quite reasonable for ecosystems because not everything communicates with everything else. Okay, and then what we have is a bunch of smaller random matrices, right? So then if we have n blocks, then the May criterion becomes n over m times c, much less than 1. So it's easier for the system to be stable like this. Now, it's a little bit cheating in the sense that when I decompose into blocks, I add a bunch of zeros. So effectively, I'm actually reducing c, right? So in that sense, naively speaking, we haven't done much, but it's worth considering this block structure specifically because when we think about ecosystems, the block structure makes a lot of sense. Okay, so what we've seen here is this paradigm shift, which involves this complexity-stability relation, more complex, less stable. And in relation to natural ecosystems that are typically stable, if you go and observe what happens, then often what you would see is either one species that interacts very weakly with many other species. Okay, so in that sense, the sigma would be small, even though the c and n could be large, right? Or conversely, you would see a species that interacts very strongly with only few species. You know, a specialized predator, right, that is very effective at eating one type of animal, but will only hunt that animal and nothing else. You know, in which case C would be very small, even though the sigma would be large, right? So when we consider natural ecosystems, they do actually follow this to a certain degree in terms of interacting weakly with many species or interacting strongly with few species. I left you yesterday with the thought about how our interconnected world appears to have become less stable because of the interconnections. And actually, a very nice comment was made that as opposed to ecosystems that gradually evolved and therefore they were assembled and they had time to deal with the connectivity and the strength of interactions and maintain their stability over time. What we had in the case of social networks, for example, is that C suddenly got ramped up very quickly before our society could evolve and handle this, and that's why a society that was stable before could be destabilized because of this rapid increase in C, and it takes time for us to catch up to this. So this is an interesting notion. And of course, this maze approach has very broad impact way beyond ecology, right? Systems biology, neuroscience, control theory, network science, and probably a lot of other disciplines as well. Okay, but there is an important caveat, and this is what's going to lead us to the general Lotka-Volterra equations. So, as was asked, and I said, this is only a stability analysis, a linear stability analysis about the fixed point. Now, a complex, nonlinear dynamical system could have many fixed points, right? It could have stable orbits, it could have a chaotic behavior, it could have all kinds of things happening. So just because this specific fixed point is unstable according to May's criterion doesn't mean that the ecosystem will collapse, right? It could move to a different fixed point that is very close by and could be quite similar, and that one would be stable. For example, one species could go extinct. Okay, so now our matrix has been reduced by one, right? And maybe that's enough for the system to be stable now, right? This is just one possible example of how the actual nonlinear dynamics are much richer than just the May stability criterion. So the May stability criterion is a local criterion for a specific fixed point, but it's not a global criterion for the long-term stability of the system as a system. Okay, and this is something that is very important to remember, right? Otherwise, it would have been too easy to just linearize about a fixed point and to get the answer, and that's it. No, these are nonlinear dynamics, okay? And you don't get the full answer just by looking locally around the fixed point. Okay, so that concludes May's chapter. Any questions before we move on? Very good. So, having handled the local stability, now we can try to consider the full dynamics of a system. Okay, and for that, we can consider generalized Lotka-Volterra equations. So I'll just call them GLV. Okay, and they have a rich history going back about 100 years. Volterra actually comes from Italy, as could be apparent by his name. And let's pause for a second and go back also to a question that was asked yesterday. How does this relate to consumer resource models? Okay, and what I answered yesterday, and I'd like to say again today, is these are somewhat parallel modeling approaches, right? When one models consumer resource models, one considers the consumers and the resources at the same time. Okay, you have two kinds of dynamical variables, a vector of resources and vector of consumers. Okay, and typically what you would do is you would have the consumers interact with each other only indirectly through the nutrient field, right? I'm taking some nutrient, therefore the other species has less nutrient, right? So we are in competition, right? I'm suppressing that other species because now it will grow more slowly because I took away some of its nutrient. But I don't actually interact directly with that species. Of course, I could add direct interaction terms to the equation, but usually people don't do that, right? Then you could have the exact opposite limit, which is the generalized Lotka-Volterra systems, where I don't care about the resources. Okay, I don't model the resources. There are not dynamical variables in my system. I only care about the direct species-species interactions. Okay, so that brings us to this. And in general, ecological networks are not random, right? They have structure. For example, they have trophic hierarchies. You have primary producers, right, that take sunlight and carbon dioxide and create food, right? You have herbivores that eat the grass, right? You have the carnivores that eat the herbivores, right? There are various trophic levels. Also, in bacterial ecosystems, you have bacteria that can do a certain reaction, and then their byproduct gets eaten by another set of bacteria who do another reaction, and so forth, all right? So this kind of structure, of course, doesn't manifest in just random matrices. Another example that we gave about non-random nature is specialized predator-prey interactions, right? Certain predators don't just randomly attack all species, but they would specialize in certain prey animals. And the structure could be very important for the dynamics. Right? And this leads us to the original Lotko-Volterra formulation, which actually came about to discuss the dynamics of hares, right? Like a rabbit, right? And lynxes, which is like a wildcat, okay, in nature. So we have the prey species, which is X. I imagine a lot of you have seen these equations in the past. Maybe like show of hands who has seen the Lotko-Volterra equations before. Yeah, basically almost everyone. Okay, but hopefully still we would learn some things about them because usually basic courses don't go so far, right? They just show the basics. Maybe this is a good time to pause for questions so far. Yeah.
This Racah-Volterra model models the dynamic of prey and predator.
Yes.
Is there any model that adds scavengers and something like?
I imagine there is. I'm not familiar with one, but I would say most probably there is. I mean, again, this is like 100 years old, so at this point, it has been investigated to death. Yeah.
Like ravens cooperate with wolves to catch the prey.
Okay.
It's a kind of scavenging. After the wolves eat the food, the ravens start eating.
Okay, so here you raised actually a very important point that I didn't plan to discuss, but since you raised it, right? So you talked about ravens and wolves cooperating versus a third species, right? So this, in fact, is a three-way interaction. It's not a two-way interaction. And turns out, and this was investigated in a very nice paper published in eLife, I think it was 2019. I can look up the exact reference. And that paper proves that pairwise interactions are not enough to encompass all sort of biological, ecological reality, right? So this is a big limit of the GLV formalism that is typically done only with pairwise interactions, but in fact, you could have 3-point interactions or 4-point interactions and so forth, and they add non-trivial behavior, right? This is not just adding more elements and getting more of the same. They could actually add qualitatively different results, right? But so far, we will stay just with pairwise interactions. Okay, any more questions? Good. Right, so what we have is the intrinsic growth rate of the prey, the predation coefficient, right? And then the delta is the efficiency of converting prey to predator. And finally, we also have a predator mortality rate. Now, one might ask, why do the predators spontaneously die when the prey doesn't? So, of course, this is just a simple model, and also its purpose was to produce oscillations, which it does. But also, ecologically speaking, being a predator is a lot more expensive than being a prey, right? In normal conditions, the prey, the rabbit, has a lot to eat and needs to invest quite little resources to get that food, right? Whereas as the predator, it's actually quite hard to hunt your food. And in fact, predators are quite vulnerable in nature, right? Like a cheetah, which is like a, fantastic predator. If it's a little bit injured, we'll just starve, right? Whereas a slightly injured rabbit could still go on quite well. Yeah, it has a higher likelihood of getting hunted, right? But at least it won't necessarily starve, right? So this is a good reason why only in these very simple, simplistic, I would say, equations, only the predator spontaneously dies. Okay, so since you're all familiar with this, then the fixed point analysis should be fairly easy and quick. We'll just go through it quickly, right? So we want to find the two null lines, right? So we can do dx to dt equals 0, right? Which has a trivial solution, x equals 0, or we can have y, which is alpha over beta. We'll call it y star. And similarly, if we do dy to dt equals 0, then we have a trivial solution of y equals 0, or the solution that x is gamma over delta. Right, and then we can do a linear stability analysis about this. So now, of course, this is the interesting non-trivial fixed point of the system. So even we can, at this point, draw it. Right, so I did put x on the x-axis here, hopefully. Let's see. Yes, I did. That's good. Right, and we have this, and we have that, and we have a fixed point. But now we want to know what happens about this fixed point. So we define the Jacobian, right, which would be just the d to dx of the alpha x minus beta xy, the d to dy of alpha x minus beta xy, and so forth, right, the d to dx of the second equation and the d to dy of the second equation. This is our Jacobian, and we take the derivatives and we plug in at x equals x star and at y equals y star to get a fully antisymmetric matrix. Or rather, that's not correct. It's not fully antisymmetric. It has an opposite sign. All right. We have the Jacobian, which has a plus here, alpha delta divided by beta here, and a minus beta gamma divided by delta here, right? So it's not antisymmetric, but this is positive and this is negative. And this is actually what we need, right? Because then the eigenvalue spectrum, of course, is that lambda squared plus, and then the beta cancels the beta, and the delta cancels the delta, and what we have is just alpha times gamma equals 0, or that lambda is plus minus I alpha gamma, right? So we have purely imaginary eigenvalues of the Jacobian, purely imaginary. Right, so since we're at this point experts in the local stability around fixed points, having visited May, then we know that there is no danger of anything shrinking or exploding if there is no real part. And what actually happens is that things will go around, all right? And so if you plot the phase plane of this, right? So you can take an initial condition, and it will go around, and it will look something like this, right? And the phase plane would be, of course, these arrows, like this. Okay, and this is a closed orbit, right? So this is a limit cycle. The system will keep cycling, and we can interpret this, right? We started here, right? Okay, so there's very few prey. Let's write this as, sorry, it's predator, and this is as prey. So here there's very few prey, but very few predators. In fact, there is less prey and less predators than this fixed point, right? This stable point. Therefore, the prey can multiply, right? There's not enough predators to eat it. So the prey increases, right? But now, since the prey has increased, now the predator has an easier life. It's easier to hunt the prey, right? So the predator starts to increase. Okay, now the predator has increased, so now the prey has a harder time because now there's lots of predators around, right? So there is a while that the predator increases, but the prey decreases, okay? But now there's too many predators, okay? Way too many predators. So now the predators cannot be supported by the low numbers of prey. So the predators go down, okay? And now we have too few predators. So the prey can thrive and multiply, right? And then the predators and so forth. So we get these oscillations, okay? And they're out of phase, right? They're not in phase. They're out of phase. This weird non-circular shape shows us that they're out of phase. Yeah. So far, questions on this? Okay, now there is something very pathological, I would say, about this simple model. I mean, it's beautiful, don't get me wrong, but the pathology is that because these are purely imaginary, then actually there is no sense of scale, right? Whatever initial condition I start with, I will find a stable orbit, right? So if I started here, there will be a stable orbit here, okay? If I started here, there will be a stable orbit here, right? Wherever I start, I end up with that stable orbit, okay? And this is a little bit pathological because essentially it would mean that the ecosystem can support an arbitrary number of a predator and a prey. It just depends on the initial conditions of the equation, right? The initial conditions. Yeah. So even though this is a lot of fun, it's and quite informative, it's not necessarily realistic. So before we make things a little bit more realistic, let's discuss what this, I mean, this is a conserved quantity, right? So what this conserved quantity is. So this is a cool mathematical trick that one can do. And actually, I taught, a few years ago, I taught these Lotka-Volterra equations and this mathematical trick. And then afterwards, I went to my own research with consumer resource models. And I was like, hey, actually, I could do the same trick there. And I did it, and I arrived to a new result, you know. So sometimes it's worth studying these sort of very old things because suddenly it gives you an idea how you can do that in a different context, right? So let's rewrite these equations. Okay, and then, so we are not mathematicians here, at least I'm not. So we can get away with doing stuff that mathematicians will, not, right? And what we're going to do is we're going to divide this equation by this equation and cancel the dt, okay? Right, so we have dy to dt divided by dx to dt. I mean, obviously there is a more principled way of doing this, but as physicists, if it works, then it's fine. Or even if it approximately works, it should be fine for us. But this actually exactly works, right? That dividing this equation by this equation gives us dy to dx. Okay, and of course, this also gives us the delta xy minus gamma y divided by the first equation. So we can take y out here, delta x minus gamma, and we can take x out here, right? And now, this equation is separable. Right? Now we can take the y here, take the dx here, and take the y here as well, right? So what we actually get is a separable differential equation, which is immediately solvable. Right? So what we get is alpha minus beta y over y dy equals delta x minus gamma over x dx. All right, so if we integrate both sides, what we get is some alpha log y minus beta y plus some c1 equals delta x minus gamma log x plus c2. But there is no sense in keeping two constants when we can suck all of C2 into C1, right, and just call it C. So this gives us this constant of motion of the system, right? Delta x minus gamma log x minus alpha log y plus beta y equals const. And this is what defines these closed fixed orbits, right? This is the constant of motion here. Okay, and that basically talks about the classical Lotka-Volterra equations. And now we are going to take things and complicate them because, as we said, this is great, but it's a little bit pathological. And anyway, this is a very specific two-species ecosystem where, in fact, we're interested in the dynamics of multi-species ecosystems that are general. Yes?
Have we ever done any experiment like isolating two species which are prey and predator and see the same result?
Well, actually, there were observations of the hares and the lynxes, I think, in Canada, that were also. So this is what motivated, I think, or maybe this is post-hoc. I'm not sure about the history here, but certainly, these oscillations were observed and can be described relatively well with this simple equation. Yeah, so there is justification for using these equations, but for very specific examples. And even then, this is not infinitely stable, right? Then you have a very bad season or a very good season or I don't know what, and the system is disturbed and you fall out of this regular pattern of oscillations. But over a period of a few years, I think, actually, these out-of-phase oscillations were observed in the two species and could be relatively well explained by this model. Yeah.
So this model doesn't have any stable fixed point. Isn't it a problem?
Well, I mean, is it a problem? I mean, we spoke about how life is cyclic, and many things in life are not constant, but changing, in some cyclic fashion. So here we have something that is changing in some cyclic fashion, right? Like, in many places, the spring is very different from the winter, right? Things change like that. So why wouldn't we have changes also in a fixed pattern?
So it's
Right?
not always desirable for us to have some stable fixed points. Yes.
No, I mean, what is desirable for us is to be able to model ecological dynamics in a parsimonious manner, right? So not using too many parameters, using just as many parameters as we need, and also being quite close to reality as we can. Of course, these are conflicting demands, right? Because reality tends to have lots of parameters. But we're trying to find the modeling sweet spot where the model describes reality quite well and yet is simple enough for us to have some intuition about, right? And yeah, just having oscillatory behavior per se, I don't think is a problem. I think the pathology here is that this constant of motion is arbitrary, right? This set of equations will support basically whatever size of oscillations that you want. And this is pathological in the sense that natural ecosystems will not do that, right? Typically, there will be some point beyond which the ecosystem will break, right? And that is not included at all in this formalism. And actually, this relates to your previous question about the negative diagonal and my answer about the carrying capacity, right? So typically, we would expect an ecosystem to have, for species in an ecosystem to have a carrying capacity, right? That if they exceed in number their carrying capacity, then they would have to shrink, right? And that's not the case here. There is nothing pulling back the system if I have too many rabbits and too many lynxes, right? They will keep oscillating like that, right? So that's exactly why the next complication that we're going to do is to introduce carrying capacity. And actually, I'll provide a spoiler. When we do that, then things will get attracted to a stable fixed point.
Because we were discussing about stability in the previous session, I want to know that this kind of dynamics is considered as stable or not stable.
Well, I would call it stable because we don't have positive, or in this case, the negative real eigenvalues. So nothing dies out or explodes exponentially, right? Things just cycle, but in a stable cycle, right?
So we have some kind of stability.
Yeah. So I would call this stable in that sense, right? I would call instability if I have a tendency, for example, the competitive exclusion principle, right? You can start off with many species, and for a while they will coexist, but actually, for M nutrients, only M species will survive, and the others will die off, right? So if you wait long enough, then you end up with fewer species than you started, right? And this is not the case here. Here you end up with as many species. You start with two species still survive. Their populations are changing with time, but in a stable manner. Right. More questions? Okay, so as we've just discussed, to address this pathology, we can introduce a carrying capacity. Okay, and what we really want to do is to limit the prey animal, right? Because, in fact, the predator is already self-limiting, right? Having this minus gamma y means that if y gets too large, then it gets pulled back, right? This is like Hooke's law, right? This is like a spring, right? If we think about this as the force, right, term, then the farther away I get from equilibrium, the stronger force I have pulling me back, right? But I don't have this here. Maybe, by the way, it's worth mentioning that if we do the phase plane here, so this point, 0, 0, is also a trivial fixed point, right? In the sense that there's no animals at all in the ecosystem, right? So nothing reproduces and nothing eats anything else, right? But then actually, if you plot the arrows, right, and the way the dynamics move, you will see that this is an unstable point in one direction, right? So if you have 0 rabbits, right, then the predator will die off because it has nothing to eat, right? But if you have 0 predators, okay, the rabbits will just explode all the way up to infinity, right? Because they have this positive, right? If y equals 0, right, and x is epsilon, right, then x will explode, right? It would flow like this. Okay, so we don't have a problem with the self-limitation of the predator, but we do have a problem with the self-limitation of the prey. So let's fix it. Let's add in a logistic term. Okay, so we take this guy, we shift this to the right a little bit. Okay, and now convention has it that one puts an R here instead of an alpha. So I'll go with the convention. And okay, the 1 does nothing. Okay, but then we have this term, which is the logistic growth term, right? So we've added one more term to the equation, and now this gentleman, K, is the carrying capacity of the prey, right? So if the prey is less than its carrying capacity, if x is less than k, then this is positive. And what we've just done is renormalize this positive number. Okay, so we've shifted the fixed point a little bit, right? But otherwise, you know, this picture, I mean, I haven't specified what is the value here. So, okay, so this shifts a little bit. Okay, but this picture remains, right? But once x exceeds k, then this becomes negative. Okay, and these are exactly the negative elements in the diagonal when we spoke about May's Jacobian, right? This is a diagonal element, right? X versus x, and now it's negative, so it's self-limiting, right? So once the species exceeds its carrying capacity, it gets pulled back to its carrying capacity level. One can think of, you know, I don't know, the rabbits eat grass or whatever. There's only so much grass available, right? You could have a situation where there's overgrazing, right? And then the rabbits starve, some of them, and their population decreases. So when you do that, this fixed point stays the same. Right, so dy to the t is 0 still gives us an x star of gamma over delta, okay? But the x to the t equals 0 now renormalizes our y star, which is r over beta, 1 minus gamma over delta k. Okay. So actually, it's this line that moves, not this line. Yeah, sorry about that. Okay, but this is the new fixed point of the system. You can see that at the limit of carrying capacity goes to infinity, right, we retrieve the classical Lotka-Volterra equations, right? I mean, obviously this is apparent here because this term disappears, but also logically speaking, if, the species is only self-limited when it's at infinity, then it's not self-limited at all, right? And of course, this disappears again here. This is an R, just to be clear. Okay. So one can study the dynamics of the fixed point. Right, so this has moved a little bit, but essentially we still have a straight line and a straight line and a fixed point. But now if one studies the stability of this, then we will see that instead of having these closed orbits, instead what we would have is a convergence. Now we might oscillate a little bit before we converge, right? So if we start here, and I have a simulation in the code and a figure here, right? But if we start here, we could go around a little bit, but we would get sucked in to this stable fixed point and stay there, okay? So on the one hand, this is fun, because now at least we don't have this pathology that the system can support an arbitrary number of predator and prey. But we've lost something in the process. We've lost the oscillatory behavior. So what can we do to regain the oscillatory behavior and yet limit the carrying capacity, right? We want to enjoy both worlds. So two very smart people thought about this. One of them, we haven't met yet, is Rosenzweig, and the other is our favorite MacArthur, the same MacArthur from the consumer research models, right? So this is 1963, and this is their model, which allows for cycles, but also allows for carrying capacity. Rx1 minus x over k. So far, this is very similar, right? And now we're going to meet a term that we should be familiar with from the chemostat. And again, this is not super surprising because chemostat, MacArthur, consumer resource models, MacArthur, right? So it wouldn't be very surprising that MacArthur knew about MacArthur's ideas. This is the form, right? And this can be brought to a monoform. So still importantly, this is a pairwise interaction. X needs to meet Y, or rather, Y needs to catch X, right, in order to eat it, okay? But then what we have here is A, which is a predation coefficient. So A, which is a predation coefficient, and we have H, which is the handling time. Right, the handling time, I mean, basically accounts for the fact that the predator takes time to catch the prey, eat the prey, digest the prey, right? It's not an instantaneous thing. And consistent with the same logic that we employed in the chemostat, we have a conservation of mass. Okay, so now for the predator to increase, we have this term, right? But also, just as we did in the chemostat, we have a conversion. You know, one rabbit doesn't equal one lynx, right? Several rabbits equals one lynx, right? So we have a conversion coefficient. This is actually what it's called, conversion efficiency. So I hope, and of course, the predator is self-limiting as before, right? So I hope that everything here makes perfect sense, right? By now in the course, none of this should surprise you. One of the homework questions, a very easy question, is to recast this in Monod form, right? It's very easy exercise, but then you get a feeling about what are the Monod coefficients, what's the Monod half max, and what's the maximal predation rate when it's, you know, reparameterized a little bit. Very easy. But hopefully you see the logic behind the saturating function. You see the logic behind the conservation of mass, and also about conversion coefficient. And we just discussed also this term, right, which is the carrying capacity for the prey. I'm curious, by the way, how many of you have seen this? Ah, okay, some, but actually quite few. Okay, yes?
What do you mean by monoform?
So the monoform that we discussed in the context of the chemostat was the C over C plus K, right? Or a so-called type 2 Holling response, right? The type 1 was linear, and the type 3 was some power larger than 1 here, right? And the type 2 is having n equals 1, right? Yes? Sorry, to put? I don't. Oh, dy as in dy. Yeah. Okay, yeah, sorry about that. But this d is a differential and this d is a parameter. I mean, this is the way I think most people write it. Actually, I think historically, if you go at the 63 paper, I think it was written a little bit differently. But these days, this is how it's written. Yeah, why is it a d and not a delta? I don't know. It could just as well be delta, right? We can put a delta here for you if you like. You know. More questions? Yes.
So now, like in the chemostat, the nutrient is the rabbit. Approximately.
Yes. Yeah. In the chemostat, the nutrient is the rabbit. A difference here is that in the chemostat, the flow in doesn't depend on x, right? C in is just a const, right? Whereas here, this is r times x. So it's not exactly the same, right? Because here, so still, right? So here, this is a sort of fun mixture between Lotko-Volterra and consumer resource, right? Because on the one hand, we're just modeling direct species-species interactions, but on the other hand, we're acknowledging the fact that the rabbit is a resource for the prey, for the predator, right? So the prey becomes a resource for the predator and is dealt with the same way as in the chemostat, but the rabbit on its own, it doesn't, you know, it has, it's limited by the carrying capacity, but it grows exponentially. It's not like there is a steady stream of rabbits from the sky, which would be the chemostat version, right? Yeah, but some analogies. Anyway, this is pretty fun. We won't analyze this because it's a lot of algebra, and I mean, what's the point? You could just do it yourself, or you can run a simulation. But the nice thing here is that you can have stable limit cycles, or not. Okay, there is actually a bifurcation in the dynamics depending on the values of the parameters, right? So this system of equations can support both, the getting sucked in to a single stable solution, and also to stable orbits depending on the parameters. And again, I mean, this is not a course in nonlinear dynamics, so we don't want to spend too much time investigating this, but it's nice to know that it exists. And also this sets the stage for the so-called generalized Lotka-Volterra equations, which in general have a whole range of behaviors. Okay, so before we move on to GLV, maybe some more questions. Okay. So now we move to the generalized Lotka-Volterra formalism, and this is a very powerful formalism. A lot of groups use it today. Actually, I was at a beautiful conference in L'Aquila, not far from Rome, last summer, and there were, I think it was 4 days of talks, and out of them, basically 2 days were just people the starting slide was the generalized Lotka-Volterra equations. So I'll say a little bit more about why that is, I think, but this is still very much a current research topic, okay? As opposed to the Rosenzweig-MacArthur from '63, which, as far as I know, isn't, or of course the classical Lotka-Volterra. Right, so we have the GLV, which is still a hot topic. And one of the reasons I think that this is a hot topic is that it lets you get away with violating the competitive exclusion principle. Right, so we said there is a paradox of the plankton, and we said that there have been all kinds of resolutions to this paradox over the ages, but nobody is quite sure about a single, resolution that says, okay, we've solved the paradox of the plankton always. There's a bunch of different ideas. We said temporal changes. We said heterogeneity. We said metabolic trade-offs and so forth, right? But you can see how scientists need to kind of, wiggle a bit, right? If you want to apply something that has a competitive exclusion principle on an ecosystem that has many more species than resource types, right? But when you go to the generalized Lotka-Volterra, since you're not actually modeling the resources, you don't bump into this competitive exclusion principle, right? So you just bypass it elegantly, which is very nice, right? It solves a big problem for theorists. This is also a powerful method and does have predictive capacity. There is a beautiful work by João Xavier's group in Sloan Kettering, where they considered changes in the gut microbiota of cancer patients who received a bone marrow transplant. And as a result, so before you receive bone marrow transplant, you have to get rid of your existing cancerous immune system, right? So you basically wipe out that person's immune system. And then, of course, they're very susceptible to infections. So then you megadose them with a cocktail of antibiotics, right? But then what happens is the stability of the gut microbiota is damaged, and quite often they can develop an infection of Clostridium difficile. It's a bacterium that lives in most of us, but is typically under control. But when you blast the ecosystem, the gut ecosystem, with a cocktail of antibiotics, it can survive these antibiotics and take over and actually kill the patient. So that's very tragic, right? That somebody with cancer goes and undergoes this crazy therapy with bone marrow transplant and antibiotics and everything, and then succumbs essentially to diarrhea, right? But this is a huge problem that kills a lot of patients. I don't remember the exact percentage, but 30 or 40% or something, incredibly high like that. So they use generalized Lotka-Volterra models on time series in order to predict what's going to happen and to improve the care for these patients, right? So this is also a predictive framework. It's not just a toy model, right? This could be used to save people's lives. Okay, so now we have I is the species index, right? So I is 1, 2, all the way to n, right? So we have n species. And this is a rather general form of it, right? We have everything depends on ni, so really you could write d log ni to dt, right, and move this here, which is actually what they did in this paper, Stein et al. And that just makes things a little bit more stable because the issue is, of course, to learn these parameters from the data, right? We have a lot of parameters in the data. We have n squared parameters. We have on the diagonal carrying capacities for each species, the ki, right? And also on the off diagonal, we have all the pairwise interaction terms. And that's n squared parameters, so that's already quite hard to learn. But then when you add also this nonlinearity, then it becomes even harder to use machine learning algorithms. Yes?
The coefficients Iij depend on an I and aj or no? There are some constant coefficients.
Oh, Aij. So I don't quite understand the answer. Yeah, I mean, Aij in general, it depends both on I and on j, right? So this is the matrix, the community matrix, right, which resembles, in principle, resembles May's Jacobian, but the key difference is that May's Jacobian was just a first order linearization about a fixed point, whereas here this is the general form of the dynamical interaction between any pair of species.
But for example, for one specific I and for one specific j, this is a constant. Yes.
Oh, okay, yeah. Yes, it's constant in time. Yes, and this is, and you're absolutely right that this is a tremendous simplification, right? Because species can interact with each other differently as the time evolves, or it could be influenced by a third or a fourth species, the existence of certain stimulants in the environment, stressors, and so forth, right? So again, this is quite simplistic, right? These are fixed pairwise interactions, whereas in nature, interactions don't have to be pairwise and certainly don't have to be fixed. You're right, yeah. But even this is hard, okay? It's hard to infer from data, and it's not easy to solve. Okay, so we'll talk a little bit about how people solve this. But in general, this is a very rich system. Okay, so some of the examples that it can do, I plotted a few. Some of the examples that it can do, right? So we can have the ni as a function of time, and you can start with various initial values, and then it could tend to some, sort of steady fixed values of the population. You can have that. I have a separate plot here. If you have three competing species, right? So if you have three competing species, then you can cook up the Aij that even if you start at some arbitrary initial values, they will end up actually oscillating. It's also quite easy to cook up an example where some species die out and only others remain. So you start with 3 species and 2 stay and 1 dies out. Okay? And finally, this can also lead to chaotic behavior. You need at least 4 species for that, but you can actually get chaos out of this. Okay? I won't plot chaos. That's a bit pointless, right? All of these are possible behaviors of this system. So this is a very rich system that can either fix all the initial species, drop some species, and keep a subset, right? It can provide oscillations. It can provide chaotic behavior. And this brings us back to the criticism of May, right? The criticism of May's criterion told us this specific fixed point is unstable with n species and sigma and c. And what did I say earlier today? I said, well, but it tells you nothing about what happens as you move away from this specific fixed point. So one thing that could happen is that you lose some species, and now n shrinks, and now you're stable, and you end up with a stable situation, right? So one way that people think about these GLV systems today is that you can start from a random ensemble of AIJs, which mathematically is more tractable because you can use tools from random matrix theory and also very advanced techniques from statistical physics like the replica trick and all kinds of dynamic mean field and things like that, averaging over different realizations of this disorder, right? So one has quite a strong tool set of tools that one can analyze a random AIJ, and then let this evolve, and you achieve something that has structure, right? Some of the AIJs become 0, some of the species disappear completely from the system, right? You flow to a situation where the AIJ has structure, right? So this, I would say, sort of very briefly, is my point of view about the state of the art when people think about generalized Lotka-Volterra systems today. There is quite an industry of physicists who, physicists love this, okay? Because they can use these advanced tools from statistical physics to average over disorder and so forth, right? So there's quite an industry of physicists who import methods from statistical physics of disordered systems in order to study the states of this system, right? And of course, we won't go into it now. It's quite involved, but hopefully I brought you to the point where you can continue there if you want. So I would like to spend the last few minutes of today to talk about these AIJs, right? Let's say that I've managed to learn AIJ from the time series data, from controlled perturbative experiments, right? Let's say I've managed to learn the AIJ. And one topic, which is a hot topic of debate right now, is, are most interactions positive or negative, right? The bacteria in the gut, do they mostly compete with each other, or do they actually mostly support with each other, or is on average, are things neutral, right? And you really have, like you often have in science, you have like different camps or maybe even cults, right, that say, no, there's mostly competitive, no, there's mostly commensal, right? And this hasn't been resolved to the best of my knowledge yet. So let's, sort of just discuss what the various AIJs mean. And there's a very nice figure that I stole from Wikipedia that explain this very well. So let's draw this figure. Right, so we have some species A, and we have a species B. Okay, and now I have here plus, 0, or minus. Right, so plus is benefit. Benefit. 0 is no effect. And minus is harm. Okay? And now we can do all kinds of plots about this, right? If both species are plus, right, so if Aij is plus and Aji is also positive, then we call this mutualism. And there is a lot of debate how much this actually exists in nature, right? If one benefits and the other doesn't care, then we call this commensalism. Okay, it comes from commensa, which means sitting at the same table together, right? So when you talk about commensals, by the way, all of these generally are called symbiosis, right? So when people think about symbiosis, they typically think that both benefit. They think about mutualism, but actually symbiosis is any relation between the pair. Okay, so what other relations do we have? So we have one that benefits and one that gets harmed, right? So you can call this parasitism. And now parasitism is extended in time, whereas predation happens at punctuated times. So I'm writing it here in parentheses. Okay. Also, what we have is, do it in yellow. You know, they basically don't affect each other at all, right? So this is just neutralism. And then there is the possibility that one species is harmed while the other is not benefited. It's a bit evil, I guess, but this is called amensalism. And finally, of course, there is the situation where they both compete for the same resource. So whenever one gains, it's always at the expense of the other, and vice versa, and this is indeed competition. The choice of colors is just to make it easier to read. There is no hidden order in the colors here. Okay, so this tells us about the relation between Aij and Aji in these generalized Lotka-Volterra equations, right? So we can really encompass all these different symbiotic relations, right, leading to incredibly rich behavior of the dynamics. And I guess the big challenge here is, first, how do we learn these parameters from data? It's not easy. And second, as people have pointed out, the fact that these parameters are fixed in time, the fact that we're limited just to pairwise interactions, and so forth, these are still simplifications, and really ecosystems would be much more complicated than that. Okay, so we have time for a couple of questions, because this is the end of this chapter. Yes?
So, just about the fitting the parameters, you're meaning that maybe there is a bit of overfitting, that we are considering a lot of parameters and so the problem is that maybe this is even too complex for what is the reality.
Well, I mean, it depends on how much data you have and what is the quality. But yeah, there's a danger of overfitting, sure. But it's not just about overfitting, right? Because if you think about overfitting in the sense of linear regression, right, then the fit itself is mathematically very tractable, okay? And you might suffer from too many parameters. but the actual fitting procedure is very well defined, whereas this is a nonlinear, dynamical, complex system. So even actually fitting, even if it's not overfitted, even just arriving at the right parameters is non-trivial, right? So converging to the right parameters is also a challenge. So these are two separate challenges. You might not have enough data of high enough quality so that you're over-parameterized, but also, even if you have enough data, it doesn't mean your fitting algorithm will converge to the right answer, right? Yeah. More questions?
It's like, how do you control the non-linearity in the system? I don't know if the carrying capacity that acts as a control factor.
I don't think you can control the nonlinearity so easily. So, I mean, let me try to answer your question in a different way. How do people solve this, right? So either by numerical simulations, which goes back basically to the fitting question, right? Because you can ask, let's evolve the parameters until my simulation best fits the data, right? This is one way you can do it. Or by resorting to approximations, okay, mean field methods and so forth that are imported from spin glass physics and this area of disordered systems in statistical physics, right? So these are, I think, the main ways that people would solve this equation, either just by brute numerical force or by mathematical approximations. So in that sense, I don't think you can control the nonlinearity in any way, principled way. Yeah. If you could, then you would be able to solve these equations much more easily. Okay, so this talks about Aij and Aji, right? So one would be, AAB and ABI, right? So if both are positive, then this would be a mutualistic interaction, right? If one species rises, then it will increase the other species, right? Well, actually, with the minus here, yeah, I mean, there is a question of sign. Let me flip the sign here, and then we'll be fine. Okay, sorry. I mean, there are various conventions for the sign. But here, now with the plus, when both are plus, right, then when one rises, the other rises, and vice versa, right? When one is minus and one is plus, then we have the predator-prey relations, right? The prey goes down, the predator goes up, okay? So we call this parasitism or predation, right? One could be 0, and the other could be positive or negative, right? If one is positive, is negative, and one is 0, then you have a mensalism, right? Where you harm the other species, but you gain no benefit yourself, right? And commensalism is when you help the other species, but you gain no benefit yourself. Okay? So that's the... Okay, one final question before, yeah?
You said that maybe we have the back season or food season, like food grain, battery, grass grows, doesn't grow. I have a question about that. Like, how do we add that to the models? Like, do you change the RI?
So yeah, I mean, you could change the carrying capacity, or yeah, you can change the intrinsic growth rate, right? This makes it even more complicated, right? Because then you have to decide how to change, and of course, I mean, you could still try to solve this brute force, right? But then approximation techniques also become much more difficult. Yeah. Okay, let's have a final question, and then we...
By writing these generalized questions, you actually lost the monoform equation, right?
Yeah. So, I mean, I don't know if it's okay. I'm pretty sure that you can, I mean, that people also write models where there is a monoform here as opposed to the simple pairwise relation. But I would say that's probably niche. Like the bulk of the community uses this because this is rich enough, right? It gives you the ability to extinct some species. It gives you the ability to create cycles. It gives you the ability to create stable systems that are stable. It even gives you chaos, right? So if you're looking for the simplest model that gives you the kind of rich behavior that you want, then this will do it. Okay, we introduced the monoform because we introduced the carrying in the Rosenzweig MacArthur model because we introduced the carrying capacity and it killed the oscillations. So then we introduced the mono to reintroduce the oscillations. Here you already can have oscillations, right? So you don't need to introduce it, but sometimes you might be justified to, but you need a good reason, right? Because you're complicating the model further, right? So you need a good reason to do it. Okay, I see that we have reached saturation for today. So tomorrow we will talk about how to measure the biodiversity of these systems. After we study their dynamics and their steady states, how to actually measure how diverse they are. And this is an intriguing question, right, with no obvious answer. Yeah.